In substitution reaction, there are four factors that have impact on the mechanism of the reaction, whether the reaction proceeds through an SN2 or an SN1 mechanism. It depends on these following factors. First, the substrate. What is the structure of the substrate? And second, what types of leaving group do we have? And third, what kind of nucleophile do we have? Is it a strong nucleophile or a weak nucleophile? And lastly, the solvent. What kind of solvent do we have? Is it polar product or polar aproduct solvent? So overall, by changing these four factors right here, we can dictate whether the reaction will proceed through an SN1 or an SN2 mechanism. And overall, this is the overview of nucleophilic substitution reaction. We have a substrate bonded to a leaving group. It is then reacted with the nucleophile, and a particular solvent is being used. And the product that is formed is when the nucleophile will come in to replace or substitute the leaving group. Thus, this is called nucleophilic substitution reaction. So now, let's focus on the first factor, the substrate, or the structure of the substrate. So we have observed that the trends in SN2 reaction is due to the steric hindrance of the transition state, which come from the structure of the substrate, while the trend in SN1 reaction is due to the carbocation stability. So therefore, the method and the primary substrate would then favor the SN2 reaction, because this is less steric. And the tertiary substrate then favor SN1 reaction, because the tertiary substrate, as it undergo the SN2 mechanism, it will produce the more stable cation. So more stable carbocation. Therefore, it favors SN1. As for method and primary, because they're less steric, they favor SN2. If we were to have a secondary substrate, in this case right here, there's no selectivity. Secondary substrate can do both SN1 and SN2 without any selectivity. And we also observe that special types of halide, for example, allylic halide and benzylic halide, can react through either an SN1 or an SN2 mechanism. So these are the structure of an allylic halide. So here there is a halogen connecting to the allylic carbon. And here would be a benzylic halide where we have the halogen bonded at the benzylic carbon. And these are some special vinyl halide and aero halide. And again, this is when the halide is bonded to this carbon in here directly. So we would then see that allylic and benzylic halide can actually undergo both SN1 and SN2. And the reason why that it can do both SN1 and SN2 is because they are not that hindered, because both of them are unhindered. Because this is a primary carbon here and a primary carbon in here. So therefore it can favor SN2. But because these are allylic and benzylic halide, once the leaving group break off, we will be able to produce the allylic and the benzylic carbocation, because they produce stabilized carbocation. Therefore they can favor SN1 mechanism as well. So they can produce stabilized carbocation. Therefore favor SN1. So allylic and benzylic halide can do SN1 and SN2. Now, vinyl halide and aero halide do not do substitution reaction. So no substitution reaction. And the reason why, the carbon in here is too rich in electron. Therefore, they are not good electrophile. and do not undergo SN1 or SN2 reaction. Let's now try a few practice problems to make sure we can analyze the structure of the substrate and be able to determine whether it would undergo an SN1 or an SN2 mechanism, or both or neither. So let's try A. Here in A, given this substrate, what kind of mechanism do you think will be predominant? So here in this case right here, this is a tertiary substrate. So it is very static. As substitution reaction, the nucleophile have to come in and attack this carbon. And in this case, because this is highly substituted, it would be difficult for it to attack directly. So therefore, it will not undergo SN2, but it will undergo SN1. And the reason why it will undergo SN1 is if the leaving group were to break off, it will form a tertiary carbocation, which is then stable, and that's why it favors the SN1 mechanism. As for B, this kind of substrate right here is a primary alkyl halide, which is not that steric, so therefore it will then favor SN2, but will not do SN1, because if it were to do SN1, it would then form the primary carbocation, which is too unstable to form, and therefore will not undergo the SN1 mechanism. As for C, this is the aryl halide. When a halide is connected directly to a benzene ring, it is called the aryl halide, and here in this case, it will not do either SN1 or SN2, so no substitution reaction. Because there's a lot of electron density in here, therefore it becomes very difficult for the nucleophile to come in and attack that carbon. And lastly, with D, this substrate right here is a tertiary substrate. So therefore, we will then see tertiary substrate will then favor SN1 mechanism, but will not do SN2. If we were to add on another example, let's say E, and we have the following. What kind of mechanism will be predominant, SN1 or SN2? So here in this case right here, we have a secondary substrate, and secondary substrate can undergo substitute reaction. However, there's no selectivity. So this can do both SN1 and SN2 mechanism. Let's now focus on the second factor, the nucleophile, and how that would affect SN1 and SN2 mechanism. So in the SN2 mechanism, the rate is dependent on the concentration of the nucleophile, and therefore the rate is then dependent on the strength of the nucleophile. What kind of nucleophile we have does matter, and a strong nucleophile would then favor SN2 mechanism. So strong nucleophile favor SN2 mechanism, because this nucleophile have to be able to attack in order to undergo substitute or SN2 mechanism. Versus in the SN1 mechanism, the rate of the reaction is not dependent on the concentration of the nucleophile. So therefore, the rate is not dependent on the strength of the nucleophile either. So a weak nucleophile would actually favor SN2. Now, but it can't be a weak nucleophile, because if the nucleophile is too weak, it will not undergo substitution reaction at all. So in here, weak, but moderately weak. Not completely weak. So here are some of the common nucleophiles, and whether they've been classified as a strong or a weak nucleophile. So anything that is rich in electron, so you got negatives, species, or good nucleophile. And the bigger they are, the stronger of a nucleophile they will be. And we can also have neutral substances as well, but providing that the nonmetal in here have low electron negativity to it and bigger in size. So in this case, sulfur, when they're neutral, they are good nucleophile as well. An example of weak nucleophile are basically neutral substances. Reagent that are neutral would be classified as weak nucleophile. And we can also see here that the fluoride is a weak nucleophile as well, even though it is rich in electron. It has high electron negativity, so therefore it's not that willing to donate electron. So therefore it would be a weak nucleophile. So strong nucleophile favor SN2 mechanism, whether the weak or a moderate nucleophile, but can't be too weak, would then favor the SN1 mechanism. Oops, please make that correction. SN1. Let's now try a few practice problems to make sure that we can analyze the structure of the nucleophile and be able to figure out whether it will favor SN1 or SN2 mechanism. So in first example A, we have an alcohol. So what kind of reaction mechanism will favor SN1 and SN2? So here in this case, we will see that alcohol, when they're neutral, they are okay. They are basically weak nucleophile. They are not completely weak. So in this case right here, they will be able to undergo substitution reaction. But they would be considered to be weak nucleophile. So in this case, this would then favor the SN1 mechanism. As for B, this is a thiol. And a thiol is a strong nucleophile. And strong nucleophile would then favor SN2. And for C, the ethoxide. So this is the conjugate base of alcohol. And in this case, they are rich in electron, so therefore they're strong nucleophile. And therefore would then favor SN2. And as for D, the hydroxide is the nucleophile, which have negative charge on it. So therefore this is a strong nucleophile, and that would then favor SN2. And lastly, in E, sodium cyanide. So this is when the carbon is negative, and this is strong nucleophile. And therefore it will then favor SN2 as well. Let's now analyze the third factor, the leaving group. So in SN1 and SN2 mechanism, they are both sensitive to the identity of the leaving group. The leaving group has to leave in order to undergo either SN1 or SN2. So if we were to have a bad leaving group, there will be no reaction at all. So no SN1 or SN2. So, but then between SN1 and SN2, SN1 is more sensitive to the leaving group compared to SN2 reaction. And the reason why is that the rate determinant step of an SN1 mechanism is the loss of the leaving group. That is its rate determinant step. So therefore, in order for it to undergo SN1 mechanism, we need the leaving group to be able to leave. So therefore, it is much more sensitive to the identity of the leaving group. And how do we know if something is a good leaving group? Normally, good leaving group are the conjugate base of strong acid. And here are the example of acid right here. So here in this case right here, the lower the pKa, then the stronger the acid would be. So low pKa equal to strong acid. And if we were the conjugate base of Hi would then be iodine. So iodine would then be a good leaving group. And HBr has a negative 9 pKa, and the conjugate base would then be the bromide. So bromide is a good leaving group as well. And now hydronium ions, its pKa is negative 2, and the conjugate base is then water. And that would also be a good leaving group as well. Versus here are some of the other substances that would be bad leaving group. So for an example, if we were to have hydroxide, that would not be a good leaving group. It maybe is an okay leaving group, but not the best kind of leaving group that are out there. And so basically, anytime that we have an oxygen, they're negative, and nitrogen, they're negative, these are bad leaving group because we know that these are not stable. We can also use aerial to determine the stability of this anion as well, or the stability of the leaving group by using aerial. In case pK value are not available, we can use aerial to determine the stability of the leaving group. The more stable the leaving group would be when it takes the electron with it, then the better it will be. So we observe that halides and the sulfonate ions are some of the most common good leaving group that are out there. And the reason why as follows. For halide, except for fluoride, iodine, bromide, and chloride, these are pretty stable. So therefore, they are good leaving group. And if we were to have sulfonate ions, for example, these are some of the sulfonate ions. This is called tosylate, and mesylate, and a triphthalate. These are stabilized through resonance. So therefore, they're good leaving group as well. So this is good Lg because of resonance. And as we encounter synthesis later, when we do synthesis, sometimes it is necessary for us to be able to convert something that is not a good leaving group into a good leaving group. For an example, if we were to have an OH group is not a good leaving group. So how can we make it into a good leaving group? The answer, we can actually react it with something else to make it into a better leaving group. For an example, if we want to do an SN1 reaction to make OH become a good leaving group, what we can do is then we can use an acid to protonate the hydroxy group, to convert that into water, and therefore now it becomes a good leaving group. For an example, let's say we have this following alcohol. Right now, this is not the best leaving group. So to make this into a good leaving group, we can then convert this, react this with water, with acid. And that would then become protonated. And now it can become a good leaving group where it can leave, and the product we will then form will be this carbocation and water. So that one method how we will be able to convert a hydroxy group into a good leaving group by reacting it with acid. And another method is to convert a hydroxy group into a different group, in this case a tosylate group. And this will be something that we would do if we were to do an SN2 reaction. For an example, let's say we have this alcohol. This alcohol right here, again, the OH group is not a good leaving group. But if we were to now take this and react this with a reagent that we call the tosyl chloride, and the structure of tosyl chloride is as follows. In the presence of pyridine, which is a solvent. So what will happen is that the alcohol will come in and attack this sulfur, because this sulfur right here is a good electrophile, and kick off this bromine group. So the substrate itself would then become as follows. So our alcohol group have now been converted into this group in here, this sulfonate group. And now this entire group would be a good leaving group. It is a much better leaving group compared to the hydroxide. So if we were to now take this and react this with a nucleophile, the nucleophile will be able to come in and attack this carbon and kick off this entire leaving group to become this product. And after the leaving group had broken up already, it would then become as follows. Because oxygen is now bonded to this sulfonate group, which can form resonance to stabilize the electron on it. So this is a resonance stabilized leaving group. And therefore, it can undergo SN2 reaction. So that would be some of the trick how to convert a hydroxy group into a good leaving group. Let's now try a few practice problems. Identify whether SN1 or SN2 mechanism is likely to occur with each of these following groups. So here in this case, this is the tosylate group. So tosylate group is a good leaving group. Therefore, it will then favor the SN2 mechanism. And here in this case, the chlorine is also a good leaving group. So we will see it can undergo SN2 mechanism as well. And here in this case right here, this is a good leaving group. However, it will then favor the SN1 mechanism. Why SN1? This has to do with the stability of the carbocation. Because this is connected to a tertiary carbon. If this were to break off, we would then form a tertiary carbocation in here. So that's why that it will undergo the SN1 mechanism. Now again, in order to do substitution reaction, the leaving group has to be a good leaving group. But depending on the structure of the substrate, what kind of carbon does the leaving group connected to? That the factor that would dictate whether it will undergo SN1 or SN2. So here in this case, we have primary substrate with leaving group. So that way it will undergo SN2. And same thing here, this is primary as well, and it is a good leaving group. And on this next example, this bromine is a good leaving group, and it connected to the tertiary carbon. So therefore, it will then favor SS1 mechanism. And similarly over here, this iodine is a good leaving group, and it connected to a tertiary carbon. So therefore, in this case right here, it would undergo SN1 mechanism as well. And on this one, the amine, this is not a good leaving group, so it will not do neither SN1 or SN2. And as for the methoxy group over here, this would do neither as well. No substitution reaction, because this is not a good leaving group. If we were to have take the amine and the ether in here, and if we were to react this with acid, we can actually convert them into better leaving group. But in the way they will not be able to undergo SN1 or SN2. Let's now summarize the last factor that can affect substitution reaction, the solvent. So we have seen already that the choice of the solvent can have a profound effect on the rate of SN1 and SN2 reaction. And the solvent can further divide it into polar product and polar A product solvent. If we were to have a polar A product solvent, this kind of solvent right here do not stabilize the nucleophile. And because it do not stabilize the nucleophile, it makes the nucleophile easily accessible or more available to react. And therefore, it will then favor the SN2 mechanism. And if we were to have the polar product solvent, we have seen already that the polar product solvent can solvate and stabilize the nucleophile. And because it can stabilize the nucleophile, it reduces the reactivity of the nucleophile. So therefore, it will then disfavor SN2 reaction. Because in SN2 reaction, the rate is dependent on the concentration or the reactivity of the nucleophile. And in this case, this reduces the reactivity of the nucleophile, thus disfavor SN2. And another effect of the polar product solvent is that they also stabilize the intermediate, the carbocation. Because when we have a carbocation, it will be able to stabilize by the polar product solvent. And therefore, it will then favor SN1 mechanism. So, A product solvent favor SN2, and polar product solvent will then favor SN1. So that's how the solvent can affect the rate, the types of reaction mechanism. And in summary, These are the four factors that can affect substitution reaction, whether it would undergo SN1 or SN2 reaction. So with regard to the substrate, what's favor SN2 would then be the metal and the primary substrate. This kind of substrate would then favor SN2. And as for SN1, the tertiary substrate would then favor SN1. And second, with regard to the nucleophile, the strong nucleophile would then favor SN2 versus a weak nucleophile would then favor SN1. And as for the leaving group, in order to undergo SN2 reaction, it has to be a good leaving group. And in order to favor SN1, they now have to be an excellent leaving group. And again, please remember that SN1 reaction mechanism is very sensitive to the identity of the leaving group because this is the rate determinant step. So we will need to have an excellent leaving group in order to undergo SN1 and a good leaving group to undergo SN2. And lastly, the solvent. The polar A product solvent will favor SN2, whereas the polar product solvent would favor SN1. So this is how we put all of these factors in one table. Let's now apply this and try some of this practice problem. So here in this case, given this substrate, the reagent, and the solvents, please predict which reaction mechanism will predominate and then draw the structure of the organic product. So here in this case, we see that we have a secondary substrate. Let's analyze the substrate first. So in this case, this is secondary. And we know that secondary can favor both SN1 and SN2. So we see here in this case, it can undergo both SN1 and SN2. And second, the nucleophile. This is a good nucleophile. So we'll then favor SN2 over SN1. And the solvent, DMSO, is a polar A product solvent. And the A product solvent will then favor SN2. And lastly, the leaving group. Bromine is a good leaving group. So in this case, it would do both. So when we check all of these boxes, we will then see that the condition that we have in here check up every box for SN2. So therefore, the major organic product would then be the SN2 product or product of SN2 reaction. So SN2 mechanism will predominate. And in this case, to now undergo SN2, the nucleophile will then come in and attack this carbon from the opposite direction. And in this case, the nucleophile will then be added to the opposite side of the leaving group. So basically on the back. And that will be the product of this reaction. And now let's try B. So in this case right here, what kind of reaction will predominate? So let's now analyze the substrate. So here in this case right here, we have a tertiary substrate. So this is the leaving group, and this carbon right here is a tertiary carbon. So here in this case right here, so we will then see the substrate will then favor the SN1 mechanism. And now the OH group, it is not a good leaving group. So therefore, it will not favor both SN1 or SN2. However, because we are reacting this with acid, so technically speaking, we can actually protonate this to make this into water. So therefore, that will now become a good leaving group. So we do have a good leaving group. So in this case right here, we can check up both of these boxes. And now the nucleophile. So here in this case right here, the nucleophile is the bromine. And that would then be a good leaving group. And the reason why is because in this reaction right here, we're not specifying the solvent, but the solvent is actually water. And in this case right here, HBr is a strong acid. So once this is dissolved in water, it can actually break apart to form the hydrogen ion and this bromine. So the nucleophile is actually the bromine. So in this case right here, we do have a good nucleophile. So we can check out both of these boxes. And lastly, In this case, water is the solvent, and water is polar product solvent, and the polar product solvent will then favor SN1. So therefore, we will see that there are more boxes that are checked off that will favor SN1 mechanism. So therefore, the major product will then be the SN1 product. And now, let's now figure out what the product would be. So in this SN1 product, the first thing that going to be happen would then be the protonation step, where the water come in, pick up the proton from the HBr to become protonated. And once this is protonated already, it becomes a good leaving group, so it can leave on its own. Again, because this is an SN1 mechanism, so the leaving group have to break off fast. And once that happens, we will then be producing this product. And followed by the nucleophile attack. So this is a tertiary carbocation. It will not undergo rearrangement since this is stabilized carbocation. And followed by the nucleophile attack, where the bromine will come in and attack this carbon. And the product that we will then form will be as follows. And in this case, since this is an SN1 mechanism, we will then form a racemic mixture. Both the R and the S will get formed. So that will be the major organic product for this reaction. Let's now try C. So in C, let's first analyze the substrate. So in this case right here, we have a primary substrate. And primary substrate would then favor both, it would then favor SN2. So this would then favor SN2. And second, sodium cyanide. This is strong nucleophile. So if we were to have strong nucleophile, that would then favor SN2 as well. So this would then favor SN2 as well. And DMF is a polar aprotic solvent, so that would then favor SN2 as well. And as for the leaving group, this is a good leaving group, so that will favor both SN1 and SN2. So this can do SN1 or SN2. But more conditions favor SN2 mechanism. So therefore, the major organic product will be the product of the SN2 reaction. So in this case, the nucleophile will then come in and attack this carbon, kick off this leaving group. So the concerted mechanism. And the product produced will be the following.